Okay, so hello everyone. My name is Cornelia. I gave a talk on CPU models 2 years ago, and now I'm back again together with Sebastian. And we want to give a big bit of an overview at what's going on with CPU models so far, where we are standing, and what's going on in the future, which problems we have hit, and which progress we have made. So basically a bit of a recap, then we'll try to talk a bit about issues on the KVM side and issues on the QEMU side and where we are going from there. So first things first, what are we actually trying to achieve? We are coming as Red Hat employees from a KVM perspective. We want to use QEMU KVM on ARM, and what we have is basically we want to be able to migrate a system to another system, which might be slightly different, either in hardware or in software or in both. And the guests should just keep running and basically see the same things like they did before. What we call this stable guest API, that means basically the guest sees the same things. The ultimate aim is to make it completely stable so they don't notice it. That's just an aim and a goal. We cannot go there, but we try to. So what has happened since 2 years ago when I first talked about this? I mean, we have been going on with ARM CPU models for a long time, and we've actually made some progress. So there's that thing in KVM called writable ID registers. We have more and more ID registers that are actually writable. We need this to be able to just configure stuff from the VMM side. On the QEMU side, not that much progress. We do have some code merged that is reordering the ID register stuff in QEMU, how it is stored, and is basically laying the groundwork for future updates there. And thanks to Shamir, we also have some code in KVM that can be used to specify a list of target CPUs for errata management. We'll talk a bit more about that later on. The thing is, not all is good. Some things are still very much a work in progress, and for some, we are still trying to figure out how to actually go about them. So on the QEMU side, for example, I have posted an RFC which allows QEMU to actually write to those ID registers. So you can basically go ahead, have a KVM host CPU, and then configure things on top of this. This is working, but still an RFC state because there are multiple issues that first need to be solved before we can make progress there. There's also an RFC out there, again, thanks to Shamir, that basically has support for handling those target CPU lists in the QEMU side. What we are thinking about, but I have no good idea yet, is what do we do with named CPU models? We only have host for now. As we all know, host CPU models are not supposed to be stable. Being able to configure them is a good first step, but what we really want is named CPU model like we have on other architectures like x86 and SV90. And we are not there yet. There are some challenges on that side. Then a really big part that is missing, this is just QEMU, but we also need management software like libvirt on top of it, because normally you do not want an end user to just compile an endless long QEMU command line just to make things fit together. We need libvirt support to actually use it, and we also need support to enable libvirt to actually use it, like finding out what's actually going on there. So we do have some things working. One example of which we had here as a working example is that this is if you use a recent kernel, use my RFC of the writable ID register configuration in QEMU, and then use this following short excerpt of the command line, with a few easy steps. But if you configure two sites like this, you can migrate from a Graviton 3 system to a Graviton 4 system and vice versa. So this is already an accomplishment. We have two quite different systems of course, with a lot of similarities, but we can really move guests between the two, and it just works. So, first progress, I guess.
So, okay, I'm going to start with a quick recap on what a migration will look like with regards to system registers. Then I will have a quick look at a couple of interesting registers. And lastly, show a bit of issues that we are facing as distribution people when customers want to migrate between different kernel versions. Okay, so let's start with the simple case, just migrating a machine between two hosts that are similar, similar hardware, similar kernel version. So the VMM would use an IOCL get rec list to retrieve the list of registers that are presented to the VM. And then iterate over each of these and use another IOCL get one rec to get the register value, and use everything and store it as the VM state. Both of these is dependent on what features the host supports, what features the kernel supports, and how the VM is configured via capability flags and stuff like that. And on the target side, the VMM would again read the VM state and use the Z1rec IOCL to make sure that the VM basically can keep its state. And since it's the same hardware, this is likely to succeed. Now the more different or interesting case that we are either have not similar hardware or not the same hardware, or a different kernel version. So the workflow is basically the same like in the slide before. But in this case, the VMM or some higher layer management software needs to find like a subset of supported features that both or all possible migration targets have. Then for the support of the VMM, there's another IOCL to retrieve the writable masks for each register to indicate what the VMM can actually change or influence. And then the VMM would use the Z1rec IOCL to basically disable features to get to the baseline that is common for all possible migration targets. Unfortunately, not all registers are writable today. I guess it would be more fair to say most of the registers are not writable today. So usually when I get my fingers on new hardware, I use like a modified kernel self-test to basically dump the list of all the registers and all their values and all the writable masks, and write them to a file and do a literal diff between what I have in store from other machines, and then I try to figure out what is actually possible to achieve and what needs work on the kernel side to enable more registers to be writable. The work to achieve this depends on the individual register. Stuff to consider are trapping mechanisms. Sorry, these are not always as fine-grained as we want them to be. There's stuff to consider from KVM side that not all the features that we need would be already implemented. Sometimes the ARM architecture makes things a bit difficult, and sometimes there's also dependencies between different registers or their feature flags. yeah, so all of this needs to consider and probably more. Okay, then let's have a quick look at a couple of interesting registers. These are the implementation ID registers, main ID register, revision ID, and auxiliary, I think, auxiliary ID register. Basically, these note who manufactured your processor and I don't know what revision the thing has and stuff like that. So it sounds easy, like it's just for your information thing that you can change. Unfortunately, these are also used for the operating system to decide what workaround for an errata it has to implement. Luckily, there's already a solution for that. The idea of that is to let the VMM provide a hypercall, so we can have multiple values for each of these registers, and logically these should be the values of all your desired migration targets. With that, an enlightened guest could then go ahead, use this hypercall, and decide to implement workaround for each of these possible erratas. With that, the VMM could then set directly one value for each of these registers that are used for the guest. That last part is gated via another capability flag. And yeah, as I said before, the kernel part for both the host and the guest is already upstream. And for QEMU, there's an RC available. And yeah, most or all of this work has been done by Shamir. Okay, and now I want to go over a couple of issues or difficulties that we are facing on the distribution side. There have been a couple of instances of accidentally exposed feature flags that were presented to the guest, but shouldn't have been. Unfortunately, we picked up those changes on the distribution side, and yeah, we will have them. Or do have them. So yeah, one example is the npem feature bits that were presented at some time to a guest without KVM support for this for the guest for this feature. Important to note is that it only affects the visibility, but so the guest would see the feature bits, but still couldn't use the feature. There was later a kernel patch that revoked the feature bits, and but to make life easier for the VMM with regards to migration, still allowed the previously presented value to be written by the Z1rec ioctl, but it would then be ignored. But with this, the change would be transparent for the VMM. There's another example, TCR2. So these reflect a couple of control registers that are used for the translation regime. Also there, it's only the visibility is affected. It's a bit different than the previous example, because in this case, it wasn't just a feature bit, but a couple of registers that landed in the list of the get_rect list ioctl that the VMM uses. But when the guest would try to access these registers without the feature being set, this would of course still be blocked. There isn't a solution for this yet, but I think in this case the idea is pretty clear. Since nothing changes on the guest side, the VMM has just to use this knowledge and apply a special code path to when this feature is not presented to the guest, but these additional registers appear in the output of the get reg list output. It just has to ignore them and not be confused when it wants to migrate the guest to a site that doesn't have these registers presented. Okay, and lastly, some stuff we already talked about yesterday with Oliver. When we have like proper feature flags as defined by QEMU, like for example pointer authentication, we can nicely disable them via the command line or for example via machine types. And yeah, I had a bit of I was thinking about what would appear when new registers turn up. Do we need a mechanism for that as well? But yesterday, Oliver confirmed that for actual proper registers, in all cases, there should be a feature bit in another register that we could disable and thus won't have the new registers. And yeah, it might be the case that this new feature bits aren't writable yet, but in this case, that would be something we had to address. There's also, especially with the patch that we mentioned multiple times from Shamir, where new pseudo firmware registers would appear. So for the hypercall bitmap, the bitmap of implemented functions, there's currently it's a new firmware register. Per default, the list of implemented functions would start as no-bit Z, but still the VMM would see an additional register, and when it would do like a downwards migration, so migrate to a kernel that doesn't have this feature, it would still see, okay, we are missing one firmware register, but also in this case, the idea would be, okay, nothing of this is implemented, so we can ignore this specific case. Okay, with that, I guess back to Con.
Okay, let's go back to the QEMU side. One issue we have for ARM, we basically go ahead and configure everything via ID registers, so via ID register values, individual values. And what other architectures do, they have feature bits usually, which you can turn on and off on the command line. And we need to bring those two a bit together. So we can have the ARM way, just do anything in registers. We can have the other way that we can use features and ID register configuration for stuff that isn't covered by features. Or we could go ahead and basically use fine-grained and have some sugaring on top that makes feature bits emulated. So kind of if you have feature foo set, you just set internally in QEMU the relevant bits in the relevant register. So coming back to the Queryton 3, Queryton 4 example from before, this is what we currently have with my RFC patches. Basically, you see it looks quite ugly. You have a lot of values you set in a bunch of ID registers. It's not very readable. It's different from what it looks like on other architectures. It has the advantage of working, but yeah. Now I try to convert some of these bits to features. We can cover quite a bit of it. One thing to note, features cannot be Boolean because some features really can have a value on ARM, unlike what might happen on x86, for example. But as you can see here, some of the values just cannot be converted. It looks ugly because it's mismatched. It is a bit nearer to other architectures because we do use features. But for example, like the Tiguan stuff, you just cannot express it via a feature. And another fun problem is if we have named model, how do we actually call them? What do we base them off? On ARM, we have such a high diversity of CPUs that are available. We have multiple vendors. Those vendors do a lot of different CPUs, and where do we start? We could start at the architecture levels. We could just simply start modeling well-known CPUs, or we could start from reference core definitions. And just to show what this will look like, I used one of my systems, which is an Ampere Mount Snow, and see what we get here. First, starting with the architecture level baseline. As you can see, lots of statements, really a lot of statements. And it's not complete. I stopped because the slide was full. So the problem is here that many of the features that are defined for 8.2 are actually optional. So they may be on or off. You do not know if you start with 8.2. There are some features that are mandatory. That's okay. There are also a lot of implementation defined registers, which you also have to specify. I don't think this is really feasible. Next thing, it's an Ampere Alpha. And let's just see what the CTR ELCO register must look like. So this is basically a real life example. We tried migration between two different Ampere Alpha CPUs, and they basically differed in that one register, which we need to configure. So good thing is it's a really nice, crisp, short command line. Bad thing is you really need to model one and all CPUs if you want to have a real baselining and a real named CPU model. And this also doesn't sound really feasible. So next one. The Mount Snow is based on the Neoverse N1 reference core. There are a number of reference cores which are quite well defined. The Cortex ones are probably the one people are most familiar with. And if we start with this one, we really only have to set a few values where the reference says, okay, it can be this or that value, and we just specify it. And it looks just much more manageable. So of course, if we start with reference cores, we still do not really cover every oddball, or like, let's tell it special CPU. For example, Apple does their own thing. They have their own baseline definition. But if we use this, we already cover a lot of CPUs because many people will just base off like one of the Cortexes or one of the Neoverses and whatever. And it looks to me to be the most manageable idea. And as Sebastian already mentioned, we also have, of course, interaction with KVM. He already mentioned the different cases there. Sometimes we can just easily enable something to make those pesky changed registers go away. Sometimes we need to apply some special workarounds in the VMM. This is something a distributor will, of course, unfortunately need to deal with, because we sometimes have the same QEMU version, same hardware, and a different KVM version. It's just how long-term service distribution work. But yeah, this needs to be solved on a case-by-case basis. And so, where are we going from here? And yeah, we have some questions like, what kind of pairings of CPUs or pools of CPUs do we actually want to focus on? The problem is here, you not want to support migrating from this low spec CPU to that completely high spec CPU, which is a completely different setup. It's just not really feasible. But if you have some really similar CPUs, like different generations of basically this same family of CPUs, it just sounds much more feasible. Then the big question is, what should the QEMU command line look like? And what should named models look like, and then we have, of course, have to implement them. And the last really big missing thing is, of course, management software support, like libvirt. If libvirt wants to manage it, it probably also needs some new interfaces to be able to figure out what it actually is supposed to manage and how is actually supposed to build such a command line and basically end up with a working configuration. So I think most of the interesting stuff in the near future will be on the user space side, actually, like in QEMU and in libvirt. So that's it. Any questions? Yep. Yeah, the question was, what is the problem with just modeling every CPU? Yes, it's just too many CPUs. You can go ahead and say, okay, this is a list of like the 50 most well-known CPUs. You will cover a lot, but then somebody comes around with a new CPU and you cannot just support it out of the box, basically.
You had the first thing where you had the E8.2 plus lots of, and from my experience with SE90, the pure size of the amount of features actually doesn't matter anymore, because that's actually it for most users. The good XML is large and the partner is large, but nobody cares because someone else is taking care of that. So I have no idea about ARM, to be honest. So my gut feeling would tell me it would be just enough to have V8 and V9, then hundreds of features, if it's possible to actually model the CPU. I don't know if it's possible. But
yeah,
that would be my approach when I saw this presentation. I have to say, I don't know.
Yeah, the question was whether we couldn't just go from the ARM V8 whatever models and just have tons and tons of feature bits. Yes, I think theoretically we could, but it would need really, we would really need to be sure to be able to discover everything, and more importantly, to be able to actually write everything. Not everything which is a difference in there is actually currently writable. If we really basically say, okay, we only have 2 neoverses, then we have a much smaller diff of registers that need to be writable and configurable. But if we try to find out something which is going to that baseline, we potentially have to deal with lots of writable CPU ID registers. And yeah, it might be a bit hard to actually figure out what we need to do there. So it's probably not impossible, but the other one looks more attractive to me, let's put it that way.
Just a follow-up question for my ignorance. When ID registers are not writable, is it hardware or software?
Why are registers not writable? It's a combination. Some are really hard to make writable. Some we haven't bothered yet. So it's a combination of the two. But for some registers, we probably do not have a good way because we would have too much heavy trapping, for example, or we would have to change something which is not actually trappable. There may be many reasons why we do not have a writable register yet.
Trying to migrate from a machine that had 48 page support to which that was, you can guess as I use page won't be able to work on the model machine. And so we can't arbitrarily write that as you go to this. No, you have to 48 pages.
The SE90 way of doing that, we will expose 64K1 and not 64K the other, and migration would not be rejected.
Yes, so that's what so happens. You have that non-write back field, enabling the
I think that's perfectly fine. You know, you do baselining with OpenStack or OpenStack, whatever.
I think all this. Sorry, Cornelia. All these ways of describing things are, I think they are all perfectly fine as long as you can describe most of the things that have something that is complete. Again, the question is, how beautiful do you want your QEMU for a life to be?
That is my first point. I think it used to be important in the past
Yeah.
Most people won't look into that are just users. Yes.
Yeah, I guess much of it is a matter of taste. It's not that it's unfeasible. My personal taste would be to go ahead with the reference course. Maybe other people have different opinions, ideas. That's completely fine. I would like to hear it, but probably not today because it seems we are out of time. But our email addresses are on the slides, and we can always discuss upstream, of course.